Good morning. This is the Getting Started video for Physics 2048 Studio, combined sections 0005 and 0006 for fall of 2020. I'm Thomas Brickner, the instructor, and let's talk about the big picture where we're heading for the semester. One of the first things that we'll work on is calculating position, velocity, and accelerations for complicated trajectories, complicated motions. The founder of physical science, Professor Galileo, back in the early 1600s, uh, was occupied by this very problem. Make an accurate calculation of the position and velocity of a projectile. And he figured out that it was a parabola, um, and a simple projectile like a cannonball or a baseball or something. He studied free fall and so forth in order to put it all together. And in the current day, we're still working on that. And um, if you have ever seen the movie Hidden Figures, you know a little bit about Katherine Johnson. This is a picture of the real Katherine Johnson. Um, and up at NASA, they still have to make accurate calculations of position and velocity. For instance, launching a spacecraft, um, transferring spacecraft between orbits, um, or re-entering the spacecraft, which is what she's famous for doing. And what I've got here is a graph of velocity versus time, and this one is the y component or vertical velocity on the vertical axis, and time is on the horizontal axis. And in this diagram, this graph, there's a thin blue line that rises from the lower left to the upper right. Now that's to represent the velocity of some imaginary projectile or imaginary object. And inside the yellow rectangle, you can see that the blue line is rising toward the right, and it's gradually getting steeper. So what that means is that the object is not changing its velocity at a constant rate. It's accelerating, and it's not a constant acceleration. In a diagram of this kind, we'll be using calculus or employing calculus in detail. And in this diagram, uh, the the derivative of the velocity versus time is the acceleration. And graphically, it would be interpreted as the slope of the tangent line to this curve. And you can see that the slope of the function, or the derivative of the function, the slope of the tangent lines to the function, are changing slightly. So this, in the yellow square, it's getting steeper and steeper. And then it kind of levels off and then starts curving around the other direction a little bit and gradually settles into almost a straight uniform acceleration. Now that's just an acceleration curve, or a velocity curve, I should say, that I made myself with the drawing tool. But those guys in NASA, like Dr. Johnson and all of her cohort, um, spent enormous amounts of brain power figuring out how to handle uh, non-constant acceleration. So the question, how do you calculate the position accurately when every second your spacecraft's acceleration is changing? That is not easy, but you will learn uh, a few basic methods that they use at NASA and that Katherine Johnson used. Another thing that we're going to talk about, and through the entire semester, is how is it that objects interact, and how is it that they interact and cause accelerations? In other words, the previous slide was about non-constant accelerations. How is it that the objects interact and cause that? Now, Sir Isaac Newton wrote his famous book, The Mathematical Principles of Natural Philosophy, thinking about the Earth-Moon interaction, starting on the first page of his book. He developed all of his 3 laws of motion for this particular problem, and it was completely successful. We will learn all about his uh, 3 laws of motion. There's a lot of calculus in it, and we're going to be hitting calculus very hard in this semester. So, buckle up for that. Here's another question, a significant question. Can an object in motion be in motion but not actually go anywhere? How do you quantify the motion of a spinning object? It's not moving from point A to point B, uh, for which one would normally use the simple distance equals speed times time idea. So, how do you tackle that? What we are going to find is that, let me start this top spinning. So this spinning top is an example of something that's not moving from point A to point B, but it's in motion. All right. So how do you handle that? How do you describe spinning motion mathematically? How do you measure it physically? And there's ways to do that, and we will be tackling that when we tackle about the middle of the semester the idea of angular momentum and inertia and moment of inertia. These are the 2 strategies, B and C, that we'll employ. Pixelate the object into small pixels of mass and then study the position and motion of each little pixel. And guess what? There's a ton of calculus in that as well. Speaking of calculus, here's a huge question. How does the simple oscillation of a spring, like a spring in your car, the coil springs in your car that you may have, or the spring, in a pen, that a little pen that you click, it's got a little spring in there, right? So how does that simple oscillation of a spring relate to the motion of all the different kinds of waves that there are? Think about it, all the different kinds of waves, light waves, radio waves, X-ray waves, seismic waves in the earth, sound waves, water waves like in this picture. So Thomas Young, who was a doctor, a medical doctor, decryptor of the Rosetta Stone, and a physicist, he made a study of oscillations in wave, and he was able to establish that light is a wave. And he was in the late 1700s, so about a century after Sir Isaac Newton. And this idea that light is a wave contradicted Sir Isaac Newton's theory that light was a particle. And Sir Isaac Newton had perfectly good reasons to think that. And they remain perfectly good reasons to think that light is a particle. And Thomas Young had perfectly good reasons to think that light is a wave. And we still wrestle with the wave and particle properties of light. Now, we'll study this early in the semester, the idea of oscillation and the calculus that describes it. And we'll bring it to culmination, the full study of wave interference and diffraction by the end of the semester. And that brings us to our first look at Planck's constant, the one constant to rule them all. It is used in every interaction in the universe. And we won't be studying quantum physics in Physics 2048, except to say that we'll be able to look at some of the things that go into quantum physics. So this will be our first good look by the end of the semester at Planck's constant. And that is going to put us into position to look forward to the theory of electromagnetism in Physics 2049. And that will allow you to understand the structure of atoms and molecules, which are all electromagnetic. And like Rosalind Franklin in 1952, what does the diffraction pattern from X-ray waves tell us about the structure of DNA? Well, this is her famous photo 51, where she took using X-rays and the diffraction of those X-rays uh, through the crystal structure of DNA, she was able to figure out, and everybody after her was able to figure out the double helix structure of DNA. So by the end of the semester, you'll be in a prime position to start grappling stuff like this in the theory of electromagnetism and all that it implies. Um, Now, let's talk about the nitty gritty. Let's get down to the nuts and bolts of the semester because I'm sure grades are on your mind. So let's talk about the basics. We are a remote synchronous class. We're not a fully online W section. All right. So that means that our class meetings are going to be what they would be if there was no emergency and we were all, milling around campus. We'd meet in Mathematical Sciences building, room 350 from 4 to 6:50 p.m. All right. Now we're not going to be doing that. We're going to be meeting online. So this is going to give you but we're still going to be meeting at that time online. So um, each class is going to be broken up into a few sub-sessions, and it'll be recorded so you can listen to them later and view them later. We'll be using the conferencing tool and also Zoom. Those are two different conferencing software packages that UCF has integrated to web courses. And so we'll be using both because they do different things. They do things slightly differently. Conferences has advantages. Zoom has advantages. So we'll be using both of them. And there'll be little 15-minute breaks between each session, approximately 15 minutes. And we might not have two Zoom sessions on a given day. We might have one big Zoom session, but it'll be roughly like this. So we'll start at 4. We'll dismiss at 6:50 p.m. But we'll have kind of shortened sub-sessions to work with. All right. Now you'll have a free textbook. It's the OpenStax Physics with Calculus textbook. It's pretty good. It is embedded directly into web courses. So you'll be able to, when you're in web courses, you'll be able to read it. You'll be able to read it outside of web courses too. I'll give you a link for that when the website opens completely on Tuesday afternoon. So it's free, so that's really good. Now, you're going to be doing homework, including written homework in web courses. All right. And the written work that we do this semester is pretty important. It'll be on homework and it'll also be on quizzes. Oops. It'll also be on quizzes and exams. So let me just get back down there. So the quizzes and exams are going to be in web courses. The homework, the written homework, the quizzes and exams will have upload problems, upload assignments, where you do a written problem and you'll have a specific amount of time to do it, just like you would in class. And you'll take a photograph of it or scan it if you have a scanner at home, and then upload it into web courses, and then we'll grade it. And you'll be able to see the graded work that you turn in. It works pretty nicely. So that's pretty important, and it will be. And one more thing to emphasize, the quizzes and the exams, you'll have a specific set of time. You won't have a full day to, slot in 60 minutes on a quiz or a test, a midterm exam. You'll have adequate time in the 4 p.m. to 6:50 p.m. Class time. And that's the way it would work if we were meeting under regular conditions. You get to class on exam day, you get to class at 4, you start the test, or you do some studying first and then you start the test. And then you dismiss when the test is over, or maybe if it's just a quiz, you have a little bit of a regular class session afterwards. But if under regular conditions, it would all happen in the PSB or MSB 350 between 4 and 6:50 p.m. Tuesday or Thursday. And so that's what we're going to be doing. So you're going to have to be um, on time, and you're not going to be able to be absent because we don't have any makeup exams. Class like this, you just can't do it. And so um, you've got to, totally engrave those in your mind. Get the schedule down. Now you can see the schedule on the syllabus page in web courses. All right. So you can schedule that out. And if you can't make it, you can't make it. Um, so drop the class and be ready to add it in another semester. I don't think there are any other classes in for Physics 2048 that'll be any that will be similar to that. I think they're all going to be doing remote examinations. All right. Now, so that's pretty important, and you absolutely have to make those dates. Now, you can miss, one or two sub-sessions of a given class day, or an entire class day, which is not good. But if you have to go to the dentist, that's important. You got to do it sometimes. But try not to schedule dentist appointments on exam days, and you'll see the schedule for it in the syllabus page in web courses. All right. Now, I mentioned that written problem solving is pretty important. Yeah, it's the gold standard for this class. Here's a homework one from a few years ago in Physics 2048. You're in a research vessel, the RV Nathaniel B. Palmer, at rest in the Norwegian Sea, halfway between Bodo, Norway, and the coast of Iceland, exactly at the place where the Greenwich Meridian crosses the Arctic Circle, etc., etc. And so this was a homework assignment to calculate, basically do a little bit of trig and some circles and figure out some distances. Now, here's my solution to it, and I made a PDF of it and provided it to the students after they turned in their problems. So you'll be seeing my solutions, and this kind of shows you what I expect of your solutions. Notice that there's clear diagrams, not too small, and not too many. I've got some, but I don't have a whole ton of diagrams. There's a few strategic sentences, and the answers are clearly marked. So if all goes well, you'll have 9 of these problems to upload. You do your best, you write clearly, um, and you'll earn points for your grade from that. And you can see what my point structure is over there. In that semester, it was 10 points per problem. We'll be doing things a little bit different. In fact, let's talk about earning points for your grade in general. Here's the basic breakdown. Um, Every task that you do generates points. Homework and class participation, that's the first two items. Um, I just described homework. Class participation, we'll be taking attendance in every subsession. So every day, every subsession, we'll be at least taking attendance, and we may have class participation uh, points as well in some manner. So we're still working on exactly how we're going to do that. So those will all be scaled down to 36 points for homework and 72 points for class participation. All right. That class participation is going to be 20% of your grade. All right. So you can't neglect any of these. I mean, if you neglect quizzes, or if you don't do any homework, for instance, that means 10% of the pointage you can't get. All right, so you have to ace everything else in order to get an A, 90%. So, and acing things in my class is not, my exams are fair, so you'll if you do a normal amount of studying, you'll be all right. You'll make out okay. You might not get an A, but you probably won't flunk it completely. But yet acing, even if you do all the study and do discussions and web courses, come to office hours and stuff, you'll still really work your tail off to ace an exam of mine, which happens every once in a while, but it ain't easy. Anyway, this is the how the points stack up. Now, homework and classwork will be scaled down because we'll have other homework than written homework. So we may have an occasional reading assignment in web courses with a few multiple choice questions and stuff like that. So that'll go into your homework grade along with the written stuff, and it'll all be scaled down to 36 points. All right. The classwork, similar. There's no way to predict how many point class participation points you're going to get. So what we'll do is scale those down percentage wise to 72. Now, quizzes and midterms and the final, those points, they're not scaled. You just get those points on the exam and that's it. All right. I never curve the grades. I don't have to. All right. And point being, most semesters, I don't really hand out a lot of Fs or Ds. The Ds are from students that don't come to lecture or to class and don't do homework, or blow off. So if you blow up, and I've had physics majors flunk for those two reasons. They blow off class, they blow off the homework. What can you do? That's it. That's a normal expectation. So if you want to get a decent grade, maybe not an A, but you want to get a decent grade, uh, be extra faithful, come into class Tuesdays and Thursdays between 4 and 6:50, and be faithful doing homework and stuff. That's all I could tell you. Because you can get good pointage. I mean, it's hard to get, an A on a final or a midterm or even a quiz sometimes. But getting the equivalent of an A in classwork and homework is easier. That's definitely an easier task. Okay, so we have 360 points altogether, two quizzes, 18 points each, midterm of 72 points. That's the big test. And then the really big test is the final, double the size of a midterm, which is my normal procedure. So the final is 40% of the grade. It's pretty big. And we don't have any dropped exams, the way we do in some intro classes. We just have these exams and you just got to make them. There's no substitute for it. There's no makeup. All right. Here's the grading scale. So you earn your points over there, the pie chart, that little table over there. And then at the end of the semester, after the final, this is how I would assign letter grades. 324 points or more, that's 90%. You get a letter grade of A. 270 points or more, letter grade of B. 216 points or more, letter grade of C. 180 points or more, that's a letter grade of D. That's half the points, 50%. C is 60%. And then below 50%, below 180 points, that's a failing grade. And unfortunately, sometimes I have students that fail, but usually it's because they're blowing off class. So don't blow off class. Get to class, do your homework. Let's see. I'm starting to sound like somebody's mother-in-law. But anyways, it's true. That's what you want to do. You want to be faithful about those things. So that's it for now. And welcome aboard. And I'll see you on Tuesday.